Hi, I'm Sepideh Karimi.
I'm Aditi Shah.
I'm Valerie Fanelle.
Hi, my name is Bharath Subramanian.
Right now, there are several challenges with audio CAPTCHAs that impair their usability for blind and visually impaired people. The existing designs narrate a series of 7 to 8 alphanumeric characters, which the user is expected to listen to and reproduce in a text box. However, in order to access the internet, audio CAPTCHA users rely on screen reading software, which echoes every character the user types as they are typing. As a result, there's overlap between the echo of the screen reader and the next character spoken in the audio challenge. We call this problem audio interference. To avoid this interference, blind users have to memorize the string of 7 to 8 numbers and letters and then reproduce them from memory. This process requires higher levels of attention and working memory. In fact, past work has found that in comparison to visual CAPTCHAs, audio CAPTCHAs take more time to solve and users are less likely to get them right. In an attempt to bridge the usability gap between audio and visual CAPTCHAs, we designed, implemented, and evaluated 4 novel audio CAPTCHA designs that were inspired by prior work and the personal experiences of one of our co-authors, Aditi, who lost her sight when she was young. The challenges we created contained variations in speed, pitch, and type of background noise. The background noises varied from public spaces like cafes to the sounds of planes and wind. As a result, these challenges complicated potential speech-to-text attacks using high randomness. In order to minimize the audio interference between screen reader transcription and the text that screen readers read aloud, we included 1 or 2 second pauses between each sound. The math, pauses, and categories designs had a 2-second pause between characters, while the character design had a 1-second pause between characters. We did this because of the quicker nature of the character design, and we were also interested in testing how users responded to shorter gaps. In our math design, we asked survey respondents to calculate a running total on equations that used addition and subtraction. This design was intended to reduce the memory burden on people with visual impairments. At each step, the user would only need to cognitively keep track of the running totals. The need to do on-demand calculations might be challenging, but by keeping the operands within single digits and limiting the total number of operations, we hypothesized that the challenge would be easier and faster than the standard or control design. In our character design, we asked respondents to count the number of times they heard one specific character throughout a string of random letters and numbers. Because this design asked users to only keep one running total in mind, we hypothesized that because this design asked users to only keep one running total in mind, we hypothesized that the reduced cognitive demands of this design would result in greater accuracy and faster input completion speeds. In pauses, we asked respondents to transcribe exactly what they heard in a string of numbers and letters. This design closely resembles the control, except it has longer pauses between each character. Pauses should also be relatively simple to deploy, given its similarities to existing audio CAPTCHAs. Finally, in the categories design, we played various sounds and asked the respondents to count the number of times they heard a sound belonging to a certain category. For example, a user might have been asked to identify the number of times they heard instruments within a stream of sounds like babies crying and birds chirping. One of the benefits of this design is that it's language agnostic, but there can still be cultural differences in category membership, which we will discuss later.
In order to understand the effectiveness of our prototypes, we conducted an IRB-approved online experiment with 67 visually impaired users from around the world. We started with collecting online open-source samples of alphanumeric characters like A to Z, words like plus and minus, and some easy-to-identify sounds like bird chirps, car honks, and even white noise. Once the samples were collected, we used Audacity, an open-source audio editing software, to create our CAPTCHAs. Audio effects and white noise were added to distort the clip's pitch, speed, and amplification, which helped us improve both the security and the ecological validity of our designs. In total, 36 novel designs and 3 control designs were created using this method. They were all 16 to 18 seconds long, with a 1-second pause at the beginning to enable users to navigate to the text box to record their answers. To conduct this experiment, we designed a web platform using HTML, jQuery, and PHP, which served as our testbed for collecting quantitative metrics and qualitative feedback from users. The website was hosted in Heroku and was made available to the participants during their scheduled time. The experiment was conducted in 3 sessions, with an interval of a week between each session to study the behavior and adaptability of the user over time. The first session was conducted over a Zoom call with the participants sharing their screen. This was done to ensure the legitimacy of the user and to help them understand the process. During the experiment, the user was provided with the control CAPTCHA first, followed by 3 sets of each novel prototype. After the completion of each prototype, the user was provided with a feedback form consisting of a Q&A to be answered in the form of Likert scale and comments to collect qualitative feedback. The testbed also collected metrics such as time of completion, number of attempts per CAPTCHA, and these furthered our quantitative analysis. To evaluate our designs, we wanted to know how our audio CAPTCHAs compared to existing audio CAPTCHAs along task performance metrics, security against common attacks, and self-reported and heuristic measures of usability. We found all 4 of our new designs to be significantly more accurate and faster than the control condition, which had a 43% accuracy with a time of 53.6 seconds. Participants completed the math condition with the most accuracy at 89%, followed by character at 87%, pauses at 76%, and then categories at 70%. As for speed, the categories prototype was the fastest, followed by math at 31.7 seconds, character at 32.7 seconds, and the control at 53.6 seconds. We also observed a learning effect across all designs where accuracy steadily increased as completion times decreased. We tested the security of our designs against 2 adversaries, a random guessing adversary and an adversary that used open source NLP models. The control and pauses designs were the strongest against random guessing, but relatively weak against NLP. The remaining prototypes, math and character, were stronger against NLP but weaker against random guessing. The character and categories prototypes were weakest against random guessing, while the math prototype was not as impacted by random guessing, but still vulnerable as its set of possible answers was a pinch distribution. Assuming a limit of 1 guess per challenge, these levels of security may be sufficient for many day-to-day use cases, given the task performance and usability improvements we made. A mixed methods usability analysis of participants' open-ended feedback and questionnaire revealed participants much preferred our prototypes to the control. Control with pauses was preferred over the control by 73% of participants, followed by character at 67%, then categories at 61%, and then math at 62%. The character prototype was rated most usable and satisfying among all of our designs. The math prototype was rated the least usable, least satisfying, and least preferred, yet it provided the highest accuracy and second highest speed. Open-ended qualitative feedback revealed participant concerns about fairness and addressing accessibility more broadly beyond visual impairments, as well as similar concerns regarding hearing loss were heavily present in our population of participants. Some participants expressed gratitude for the increased pauses between characters, while others were most polarized on the categories prototype. Some found categories to be too vague, yet participants outside the US really liked it. All of our designs outperformed the control in key measures, but there was no single best design. Use case matters. Math was the most accurate, character was rated most usable, pauses was most preferred over the control, and categories was fastest and most global. These improvements came at the expense of increased vulnerability against random guessing, but this seems to be a reasonable trade-off. Thank you for listening, and here's how to contact us.